Hello everyone and welcome back. My name is Sumit and we are doing the operation management paper together. We have done a certain number of topics, and like I told you, what we are going to do is we are going to finish off the small topics so that we can dig in to the larger topics at the end of it. What we are how an operations paper is designed is, or how I look at it is, it's done in three parts. The first part is setting up of a plant. The second part is running the plant, and the third part is what I'm going to introduce one at a time. Like for example, when you talk about forecasting or location planning or facility planning, all this happens in setting up the plant. What machine to buy, how many machines to buy, and all of that. Once you've understood what your required capacities, you've bought a few machines, and now you are running the plant, so everything is going well. So productivity planning and productivity management, capacity planning, all that comes in the running part of the organization. Once the organization is set up and it's up and running, we now come to making it better. And that phase, according to me, is called the optimization phase. What do you do in the optimization phase? Well, in the optimization phase, you've set something up, it's working well, but now you are trying to find ways of making something better, easier, faster, more productive, so that I can get more money out of it. And that is what we are going to now slowly and gradually move into. Later, we are completely going to move into optimization. But before you move into optimization, you need to study the current processes of your organization. Like productivity planning and productivity management, or utilization and efficiency planning, is nothing else but trying to find out how well is your organization running now. So that if there is a scope for me to make this better, I will try and make it better in some way or the other. The next topic that I want to do in this section is called queuing theory. What is queuing theory? As literally as the name goes, queuing theory. It is a concept that is going to deal with queues. As an organization, depending on what kind of an organization you are, remember we did scheduling. Scheduling was also queuing, but it was queuing of the jobs. Here we are literally talking about queuing of people. Well, you can also do jobs, but we are going to talk about queuing of people. Queuing of people where, or queuing of people why? Whenever you are an organization that provides, let's say for example, you are Vodafone and you provide service, and then you provide post-sale service also, which is you provide customer support. You want to change your SIM card, you want to change your plan, you want to know more about your bill, you want to change your scheme, whatever you want to do. Now, if I set up a customer service center, customers will come to my service center, take whatever service they have to, and leave. It is not always that a customer walks in and I have my customer service manager available to give them service. This is where you will have to form a queue. So my customer comes and sits in a queue, and as soon as it is that person's chance, the customer goes, takes service and leaves. Another example, doctor. Again, not a doctor that calls you an appointment. The doctor that calls you without or you go to the doctor without an appointment. You go, you see the people sitting there, you sit in the queue and you move on. Now these queues are of different types. Like there is one kind of a queue where you literally form a queue. Like for example, taking a ticket at a railway station, you literally form a queue. Now, when you talk about you go to a customer service center, you don't literally form a queue. What you do is you get a token number, and then the token number is in queue. Now, whenever your token number is called, this also happens in banks, you go to the respective token window and you get your services and you move out. But eventually a queue is formed, whether it's a literal queue or it's a figurative queue or it's a digital queue. There is a queue. Now, if the rate at what you are serving people is slow, the queue formed will keep getting bigger. And if the queue formed keeps getting bigger, your customers will not get served on time and they will be disappointed about your service. So you also must have heard that अरे वो वोडाफोन का कस्टमर सर्विस घटिया है, मैं गया था 4 घंटा लग गया. Another very good example of queuing system is a petrol pump. Imagine there is a petrol pump with only one pump. What do you mean by one pump? A petrol pump has different pumps where there are different number of people standing. But if you go to like a remote village or a remote highway where there is not too much of a vehicle traffic, they usually have just one pump and one person manning the pump. Now there you form a queue behind the other. And as and how one person gets served, the other person keeps moving on and starts taking service. Now if the person serving at the pump is very slow or takes a lot of time or is not efficient enough, the queue will keep getting bigger. And after a while, people will look at the queue and say, let it be, let's fill up at the next petrol pump, not here. And they will move on to the next petrol pump. Isn't that an indirect loss for you? And that is exactly what we are going to study in this section, and that is a queuing model. When a queue is formed in an organization of people who come to take some kind of a service, what all goes through the queue, what can I understand about the queue, how can I make my service better so that people who come to take my service don't have to go without taking the service, or they get service quicker or they get service quickly. We have seen different people implementing different models. Like you've also seen these roadside chart centers where initially it was you pay, you eat and you leave. Now you take a token at one window and then you go and stand in the respective section. You give them the token, you eat and you leave. So there are different ways in which people are trying to make their organizations better so that when people come to take service, they get service quicker and nobody has to go without service. In queuing theory, we are going to learn that if I am an organization that provides service, what is going on in my current organization as far as service providing is concerned, and how can I make it better? Is there a scope of making it better in any way? A few things that are very important when you decide to get into a sector where you are providing some kind of a service. Now, when I say service, I literally don't mean that you are a service center, or I don't mean that you are a customer care center only. It could be the ticketing counter at a railway station. The ticketing counter is my service station where people come to take service, and that service is called buying a ticket. Or it could be, nowadays we are very particular with the pandemic and the current situation that is going on. Even at medical stores, they don't randomly let you in. Even at medical stores, you are asked to stand in a queue with social distancing. So here also I am trying to understand how people will come, how will they take service and they will leave. So if you are into this kind of an industry where a queue is formed, there are two very important things that you need to know. Number one is the arrival of people, and number two is the rate of service. These two very important things will tell you everything you need to know about your organization's queuing system. One is arrival, we call it lambda, and one is service and we call it mu. Lambda and mu are these notifications given to arrival rate and service rate. So you need to tell me at what rate do people come to take service and at what rate am I providing service. Like for example, you tell me that in 1 hour, in a given hour, in 1 hour, there are 3 people that come to take service. Okay. What potential do you have of serving? Well, I have a service system that can provide service to 5 people per hour. Fantastic. So on an average, only 3 people come to your service station, but you have a service rate of 5 per hour. So all 3 that come to you will definitely get service. It could also happen that people are arriving at your service center at a rate of 4 per hour. And you are capable of providing service at the rate of, let's say, 5 per hour. Well, this is also nice. No problem. So every hour I am estimating 4 people will come in. And I have the capacity of serving 5 people. Like for example, you are trying to tell me that every 15 minutes one person will come for service. Yes, that is what I am telling you. But I can provide service at the rate of 12 minutes per person. How do you know that? Well, 5 in 1 hour, no. If 5 people get served in 1 hour, which means 5 people are getting served in 60 minutes. So 60 divided by 5, you are spending 12 minutes to serve every person, and people are coming in at a rate of 15 minutes per person. So first person will come in, next person will come after 15 minutes, and within those 15 minutes I will serve the first person and that person will leave. What if I tell you that customers are arriving at a rate of 7 per hour and your rate of service is 5 per hour? I will say there is something very terrible about your servicing system. Why? Well, because if people are arriving at a rate of 7 per hour, every hour 7 people come to take service from me. But in every hour, how many people can you provide service for? Well, only 5. Well, if you can provide service for only 5, sir, there is something terribly wrong with your system, because every hour there will be 2 people who will not get service. If your service center is available for 8 hours in a day, every hour 2 people will be left out of service. In an 8-hour day, 16 people will be left without service. So 16 people will be denied service. And that, my friend, is the most pathetic customer system that you've put up. If you are not able to provide service to 16 people in one day, what good is your system? So the first thing that you need to remember is that if you are going to provide a service of any kind, study and find out at what rate do people come to take service from you. If people come to take service at the rate of 3 per hour, make sure that the rate at what you can serve them is 3 or more than 3 per hour. Because if your service rate is less than 3, people will end up getting denied of service. And if that happens, then your service system is not functioning well, or it is not agreeing to, or it is not fulfilling the basic need of a system, and that is providing service. So if lambda is the arrival rate and mu is the service rate, then I need to make sure that always and always lambda is less than mu, and that is your arrival is smaller than your service. If your arrival is more than your service, do something. Put up another service station, because people are being denied service. People cannot be denied service. Increase your rate of service. So it should always and always be that the ratio between lambda and mu, also known as rho, R-H-O. It's a Greek letter. I'll tell you how to draw it. It is a P, but it's a P with a lot of curves. A lot of people draw it like this also. I don't. This is how I draw it. Rho, R-H-O. This ratio between arrival and service, if arrival is always less than service, which means numerator will always be smaller than denominator. If numerator is always smaller than denominator, then this ratio should always be less than 1. If this ratio becomes greater than 1, I am sorry, but your service system is pathetic and it is not an efficient service system. If customers have to come and leave without getting served, I'm sorry, but your service system is not a good service system. So you will always make sure that the arrival is always lesser than the service rate. And if that happens, then lambda upon mu is less than 1, which means the value of rho is always and always less than 1. If lambda is less than mu, which means that arrival is always lesser than service. If people arrive at the rate of 4 per hour, my service rate is I can serve 6 per hour. So 4 I can definitely serve in that 1 hour. So there is nobody who is denied service in any way. Yes, perfect. But sir, if you are telling me that arrival is happening at the rate of 3 per hour and service is being given at the rate of 5 per hour, can I say something? Yeah, what? Then why is a queue formed? See, queues are formed when people are getting service. There is no service center or station available. So people have to form a queue. If you are telling me that in every hour only 3 people come in, but I can serve 5 people, then why is there a queue being formed? Well, I'll tell you. This arrival rate that you are talking about and this service rate that you are talking about is not an exact service rate. That is why we are doing it in management and statistics. No, this comes under management in statistics. We are doing management where we are managing something with the help of statistics. See, when I tell you that people are arriving at the rate of 3 per hour, in 1 hour 3 people, which means every 20 minutes one person has to come. Am I right? So I open the shop, 20 minutes the first person comes, then 40 minutes the second person comes, then 60 minutes the third person comes. That is what it says, and that is what it means. When you tell me that the arrival rate is 3 per hour, what I understand is that every 20 minutes one person comes in. I agree. But that's not literally true. I'll give you a small example for this. Sometimes if you go to like a petrol pump or a doctor and you realize that, oh, when I came here, there were like literally one person. And now 5 minutes in and there are like 15 people already in the queue and I am ahead. Thank God I came 5 minutes early. So let's say this happened. 15 people came in a total span of 3 hours. 15 people came in a total span of 3 hours. Fine. 3 hours is 3 into 60, which is 180 minutes. 180 minutes divided amongst 15 people is 12 minutes per person. So are you trying to tell me that you were looking at your watch and 12 minutes first person walked in? Exactly another 12 minutes second person walked in. Exactly another 12 minutes third person walked in. That is not how it works. See, I have given you an average. People enter at an average rate of 3 per hour. It could happen that 3 per hour is in an hour 3 people. So in, let's say 5 hours, 15 people. Does that mean that these 15 people enter at an exact time? No. It could happen that I opened the store and immediately 15 people walked in. Or it could happen that I opened the store, first 1 hour there was nobody, second hour there was only one person, third hour there were 4 people. So up till the third hour there were only 5 people that are done. In the fourth hour all the rest of the 10 people came in and in the fifth hour there was no one. So when I tell you that 3 people per hour come to me for service on an average, I am not saying exactly 3 people will come. What have I done? I have studied the arrival pattern for days together. Every day I sat down and I checked how many people came to take service. I wrote down day 1, first hour so many people, second hour so many people. Or I said day 1, 8 hours the store is open, first day 20 people, second day 40 people, third day 15 people, fourth day 60 people, fifth day 8 people. And at the end of all of it, I did a total for the total number of hours and then I took an average as to on an average how many people do I expect per hour. Similarly, when I tell you that people are getting served at a rate of 5 per hour, which means if this is a doctor, the doctor attends 5 people every hour. 5 people every hour means 5 people in 60 minutes. 60 minutes divided by 5 is 12 minutes. So you are trying to tell me that this doctor treats every patient in exactly 12 minutes. No. And we've seen this, we've ourselves seen this in a doctor's clinic. Some person walks in and he or she only wants to show. So they had already come yesterday. They took a blood. The doctor said do one thing, take an x-ray, do a blood test, do blah 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 and so on and come tomorrow. They've come today. All they are going to do is show reports and the doctor is going to write them a prescription. That's it. Hardly takes more than 5 minutes. But the second person that has come in had gotten stitches. And now he's come today to remove those stitches. Is the person going to be out in 5 minutes? Definitely not. This person is going to take more time than other people. There was another person who said, I'm just here to get a general checkup done and I want a medical certificate. So the doctor sits him down, checks him, basic cough, cold, so on, writes down a medical certificate. Barely happened in like, and that too he says, go take the medical certificate from my secretary or my PA or my compounder outside. And the person walks out, takes a medical certificate and leaves in like 2 minutes. Another person comes in and this person looks terribly ill. Coming to the doctor for the first time. This person will go into the cabin. The doctor will put the person on the whatever the examination bed is, he will check them for temperature, for oral infections, for any reflexes. They check their weight sometimes, they check blood pressure. After all of that, they will ask them symptoms, then write them a few tablets for these days, and they will write them down some tests and ask them to come the next day. This will take a little bit of time than normal. So when I say that the doctor treats 5 people an hour, which means approximately in 12 minutes, the doctor can treat 1 patient, I don't exactly and literally mean that. What I have done is, over the days or over the months, I have written down data that today how many people came in to get service. Today how many people came to get in service. Or what I did is, I wrote down patient number 1. As soon as the patient entered the doctor's cabin, I pressed start. As soon as the patient walked out, I pressed stop. I wrote down the timing. Patient number 2, I wrote down the timing. Patient number 3, I wrote down the timing. Patient number 4, I wrote down the timing. This I did for 100 patients, and I realized that in a total of 1200 hours, 100 patients were given service. So if 100 patients were given service in 1200 hours, which means it is basically 1200 minutes, then it's basically 12 minutes per patient. If I can serve 12 minutes per patient, give and take, some might take more, some might take less, an average of 12 minutes per person, which means that in a given hour, I can give service to 5 people. And because the arrival of people and the service that I am providing is not an exact value, it is a random value. That is why a queue gets formed in this kind of a queuing system. So let's go back and let me tell you this, but in a few lines now. Whenever you are providing any kind of a service, whether you are a doctor, you have a petrol pump, or you have a medical store, where people are forming queues outside, the 2 things that you need to know is your arrival rate and your service rate. The arrival rate is given by lambda per hour and the service rate is given by mu per hour. This arrival rate and this service rate is always and always a per hour rate. You never give me anything else. If you give me anything else, I will change it to per hour. Don't tell me that 15% people arrive in 5 hours. No. Tell me how many per hour. If you don't tell me, I will convert it and find it out. The arrival and the service should always follow a relationship, and that is arrival should always be less than rate of service. Because if rate of arrival is more than rate of service, people will end up not getting served, which is not a good thing for a service station. How stupid is it that you have a service station and you cannot serve people? If the value of lambda is always less than mu, then the value of rho, which is the ratio between lambda upon mu, should always be less than 1. But sir, if lambda is always less than mu, I can serve more people than that come. Why does a queue get formed? Well, a queue gets formed because either arrival or service is always random. What we have done is, we have tried to get a value out of this randomness. This value is a probabilistic value. It is not a deterministic. It's not an exact value. So, a quick. People arrive at a service station at the rate of lambda per hour and they get served at the rate of mu per hour. The ratio between lambda and mu, which is lambda upon mu, should always and always be less than 1. If it becomes greater than 1, your queuing system is not a good queuing system. Now that you've understood 1 and 2, how do I estimate the value of lambda and how do I estimate the value of mu? Well, simple. Every study that you do, so before you start understanding a queuing system, what you will do is you will sit in your system and you will start observing things. When you start observing arrival pattern, what you will do is you will say R1, how many people came to take service? Now, it's not compulsory that always only one person will come to take service. Multiple people can come together also. Like, I'll give you an example. Is it possible that two bikers together enter into a petrol pump? Yes. Am I right? Is it possible that from a family, there are three people who are unwell? If there's probably something viral, one person caught it, so other two people also caught it, also known as corona. But if other two or three people caught it, can I say all three will come together to the doctor's clinic? So what I do is I write down R1, R2, R3, R4, and in the first R, 3 people walked in together, 5 people walked in together, 1, 2, 3 people came separately, whatever it is. Whenever any kind of a study is done, to estimate something out of the study, like for example, if I gather the salaries of people in India, I want to get some consensus out of it. No, that is why I take an average. And then I can declare that, oh, the average salary of people in India is so and so. That average salary or that salary of a person in India is supposed to follow a certain pattern. We call that pattern a distribution. There are different kinds of distributions. We assume that arrival happens with Poisson distribution. And arrival is always studied as how many people enter at a given hour. So if I don't want to waste too much time and go too much back, but if you've done math in the 11th and the 12th standard, in the 12th standard you did something called as binomial distribution. Any data set that only takes 2 values is binomial, and then extension of binomial was Poisson distribution or Poisson distribution. What did you understand in Poisson distribution? Here again data takes 2 values, but the chances of one happening from the other are very less. I will tell you the kind of questions that you did in it directly. If the chance of an accident on this particular road, or on an average there are 5 accidents on this road, what is the probability that there will be at least 2 accidents, at least 3 accidents, there will be 4 accidents? I found the average number of defectives in this given lot is 7. What is the probability that in a lot of 100 articles there will be 5 defective? So what are you trying to estimate? You are trying to estimate the chances of how many number of defects will be there, or how many number of accidents will be there. And that is what arrival is. Arrival is also Poisson distributed, where we are trying to find out that in a given hour, how many people are entering the system. At the same time, in service, we don't study how many people are getting service every hour. We are trying to study so here we are dealing with number. Here in service, we don't try to understand how many people get or take service per hour. We try to understand what time does it take for a person to take service. So here we try to understand in a given hour how many people come to take service. Here we try to understand the person that comes to take service takes how long to get that service. And that is why this is time based, and time based data is assumed to follow exponential distribution. I'm going to say a lot of things. All I want you to do is chill, sit, get a glass of juice or a glass of water, get some popcorn till the time I'm talking, and just listen to what I'm saying. All this, frankly, nobody is going to ask you. But then because I'm teaching you a topic and all these elements are going to be, I could spend like 10 minutes in showing you there are 4 formulas, that's it. If I show you those 4 formulas and start with questions, we can start with questions. But I don't want to do that. I want you to understand what the concept means, what the concept is. Arrival is happening at the rate of lambda per hour. This arrival is random, and we assume that this randomness has a pattern to it. We have tried to estimate the pattern, and that pattern is said to be Poisson distributed or Poisson distributed. Service happens at the rate of mu per hour. Service is also random. There is no fixed time of service. This service, which is the time it takes for on an average for a person to get served, is said to be exponentially distributed. Both arrival as well as service, whether Poisson or exponentially distributed, we say they follow something called as a memory-less property. Now, memory-less property is like a very core statistical concept, and I don't want you to tell you, I don't want to give you the statistical definitions of it because they're of no use to you. Let me give you a, let me try to tell you literally, if you take it literally, what does memory-less mean? Well, this is what it means. I'll give you a difference between 2 doctors, one doctor that only calls you on appointment and the other doctor that does no appointment, you randomly walk in. Let's come to the first doctor. The clinic opens. Is there a time when the first patient will come in? No. Okay. Can you tell me when the next patient will come in? No, because everything is very random. But when you talk about a doctor who only takes patients on appointments, can I say if the first person walks in at 8 a.m. dot, and this doctor is the kind of a doctor who keeps a 20-minute buffer and calls in his patients, can I say the next patient, I am dead sure, has to walk in at 8:20? And we obviously talk about a standard system here. We are not talking about the person is going to be late or early. No. Next person, time given to him or her is 8:20. Can I say the first person's arrival and the second person's arrival are sharing a memory with each other? Or can I say there is a dependence of the second person's arrival on the first person's arrival? They share a memory with each other. If the first person was given an appointment of 8:10, then the second will be given an appointment of 8:30. I know, because that is how this doctor works. But when you talk about a doctor who does not call you in on the basis of this time-based appointment, you can walk in anytime you want to. There, the person who came before you and you have nothing to do with each other. You all are not sharing a memory of any kind. And that is why we say exponentially is always memoryless. But Poisson here also we say follows the memoryless property. This comes under a section called the Markov's chain. But let's not get into, like I said, the depths of that. It follows a memoryless property. Sir, I understood how arrival can be memoryless. How can service be memoryless? I can tell you. A patient comes in. Now, if the patient comes in, the doctor has to give him or her, let's say it's a kid who's fallen somewhere. So he or she has gotten a wound and the doctor is going to examine the wound and then find out if there are stitches required or whatever. So all this took like half an hour. Do you guarantee me that the next patient that is going to come in is also going to require all this only? No. But can you guarantee me that when a doctor calls you an appointment, and if you tell the doctor, if this is a dentist, if you tell the dentist that you want to get a root canal done, you know what the doctor does? He or she plans all the root canals together. So they tell you don't come tomorrow because see, as it is, dental problems are not like have to be done today. They say come tomorrow, I have 2 root canals lined up, we will finish all root canals together. They get to efficiently use their resources. Now here, all the patients are getting the same service done. Aren't they sharing the same memory? Because the process is the same. But we assume that even if it is a doctor, it is not a doctor who is doing the same procedure on everyone. It is different. If I go to a petrol pump, because the first person filled in $100 worth of petrol, does that mean the second person will also fill in exactly $100 worth of petrol? No. But in the lockdown, If everybody was told that you can only get 100 rupees worth of petrol, everybody will only get 100 rupees worth of petrol. There's no question asked there. There is a memory shared. And that is what you mean by memory less. Or don't try to remember all of that. Just try to remember one basic thing, is that when the previous person came has nothing to do with when the next person will come. How long it took for this person to take service has nothing to do with how long it will take for the next person to get service. So a quick recap. In your customer service system where you are providing service, people arrive at a rate of lambda per hour and get served at a rate of mu per hour. The arrival and the service both are completely random, but we try to understand the pattern in them, and then we say that arrival happens with Poisson distribution and exponential happens and service happens at an exponential distribution, but both follow a memoryless property. The arrival is always less than the service rate, but even then, because the arrival and the services are random, there will be a queue formed in your system. From all of this, all I want you to take is one thing. Arrival is lambda and service is mu, and arrival is always less than service. That's it. So as I move on, let's now understand a queuing system, or let's literally look at how a queue is formed. Our Indian queuing system, like for example, the queuing system that is seen outside in a railway station ticket counter, is the worst queuing system you will ever see, is the stupidest queuing system you will ever see. Why? All counters are the same? Yes. All counters are doing everything? Yes. So all counters are giving you normal tickets, platform tickets, local tickets, non-reservation based long distance tickets. So I can go to the other station and say I want a ticket to Surat. I will get one. I can get into any train that is available. So I'm talking about these. Reservation counters are different. These are ticketing counters. The same counter gives you a pass. The same counter renews your pass. The same counter makes your identity card if one is required. But this is the queue that we form. These are your service centers. Let's say there are 4 service stations. Service station number 1, 2, 3, 4. What we do is, like stupid people, we start making queues in front of every counter. But sir, what is wrong with this? Everything. Everything about this is wrong. Every counter is giving you the same service. Every counter is capable of providing you the same service. If every counter is giving you the same service, if every counter is capable of providing you the same service, why form so many queues? The most effective queue that is going to be formed is not this, but this. We do not make a queue vertically in front of the service systems. We create a single queue in front of all of them horizontally. Just because there are 4 service centers doesn't mean you make 4 queues. You stand horizontally in front of the counters. And this we have all done. When we go to temples or mosques or churches to pray, and if it's a special occasion, there are these queues that are formed. There's one God, fortunately, and we all have to go to the same God and move on. Why is this better? I'll tell you. As soon as a counter is available, so there is a person standing here, there is a person getting service here. As soon as a counter is available, this person will move on and go and stand at that counter. The queue moves like this, and the queue is going to move like this. So people join here, keep walking as and how we move on. But sir, what difference does it make? I'll tell you. Remember in a queue where you are standing and then suddenly you think that your queue is only moving slowly. So then you leave this queue and then you join this queue. And then you realize this queue also is moving slow. Then you leave this queue and then you join this queue. And then you say, okay, fine, this queue is moving faster. But little do you know that as soon as you are going to come to the window, that person in front of you is going to renew his or her pass. And that is going to take a lot of time. Or the service center stopped working. The server stopped on this system. So the ticketing stopped. Or the very famous, where they have this one huge plywood board with them, plank, which they just move in front of the window and say, "Band ho gaya." And then everybody starts running, "Kidhar jaun, kidhar jaun." And then people start joining the queues. Why is this important? Don't do this. Make a single queue. What happens when you make a single queue is, this person goes here, now this person is getting service. Now suddenly if this service center shuts down, it's okay. When this person leaves, I will go to this queue, this center. Or if this person leaves early, I will go and stand here. So nobody has to wait behind any one person for no reason. And from here, we are going to assume one very important thing. No matter how many service centers you have, you will always and always be making one and only one queue outside the service centers. Even if there are 10 service centers, there will be one queue. People will start walking to the respective service centers as and how a service center is available. Which brings us to three very important things that you need to know to assume that they will never happen. And that is, number one, balking. What do you mean by balking? Imagine that you want to watch a movie. What you decide is that, let's say this is the time and age where there was no Book My Show. What you decide to do is that you say, I have a lecture at 3 o'clock. What I will do is, usually takes like 1 hour for me to reach my class or my college. I will leave 1 more hour early, go to the closest theater next to my house, book a ticket and then go to class or college, wherever I have to go. Now you leave, you reach class or college, you reach the theater, and then you see this giant queue outside the box office. And when you ask someone, they say, okay, there is some problem or they are on lunch or something has happened because of which they are not giving tickets right now. Now you look at the queue, this is such a big queue. If I stand in this line, I am sure that I will miss college or class. Obviously, movies are important, college and class will keep happening, so you stand in the queue. But if it is somebody who thinks that no, going to class or college is important, will leave the system. And that is called balking. Balking is leaving the system before joining. You come to the system, you realize that you will not get service and you leave. Is called balking. Balking can be of two types. One can be forced balking and one can be unforced balking. What do you mean by forced and what do you mean by unforced balking? What does balking mean? You leave without joining the queue, or you leave without even becoming a part of the system. So when you are leaving, the question is, did you leave yourself or were you asked to leave? Well, in this example that I gave you, I left by myself. Nobody had to tell me to leave. And that is unforced balking. Then what is forced balking? Suppose you want to get your car washed or you want to get your bike washed. You go to a bike washing service center. Now you go there and then the mechanic says, sir, it's already like 3 o'clock. I shut down by 5 o'clock and I still have 5 bikes pending. They're still in queue. I don't think I will be able to do your bike today. Question, did you join the queue? No. You left? Yes. You left by yourself or the guy asked you to leave? The guy asked me to leave. I was willing to leave my bike. Then that is forced bulking. When you leave without joining the system on your own wish, then it is unforced bulking. But if somebody asks you to not join the system, then it is forced bulking. If you go to a doctor at, let's say, 9 o'clock, and then the compounder on your face tells you, sorry, there are already 10 patients inside and the doctor shuts down at 10, we won't be able to serve you today. Thank you for your time. You have to leave. You, if given a chance, you would definitely want to go and get the service. But then the person doesn't let you. You are asked to leave without joining the system. So what is bulking? Bulking is leaving the system even before you can join it. Bulking can be unforced and forced. When you leave by yourself, it is unforced. When somebody asks you to leave, even though you want to join the system, it is forced bulking. The second thing that we need to know is reneging. What is reneging? Reneging is same example, the ticket example that I gave you. You reach the theater, there is a box office and you are getting tickets. Now you are getting tickets, you stand in the queue. You stand in the queue and the queue is moving and suddenly one person took 10 tickets. Took the tickets, started walking out and then realized, 1 minute, I asked for tomorrow's tickets. These are day after tomorrow's tickets. Goes back to the counter, starts fighting. Now the guy says, आपने परसों बोला था. This guy says, नहीं मैंने कल का बोला था. नहीं आपने Saturday बोला था. नहीं आपने Friday बोला था. And a fight breaks out. You joined the system. You stood on the system for around 10-15 minutes. And after the fight broke out, you said, you know what? I don't think I will be able to get a ticket today. And you leave. Or you come, there is no fight. You stand in the queue. The queue is progressing. But it is not progressing as fast as it should. It is already 45 minutes into you standing in the queue, and ever since then only 4 people have gotten served and there are like still 10 people standing in front of you. You calculate for yourself that I will not be able to get a ticket today. I can, but then I will have to bunk class or college and I have to leave. So you leave, but you leave after joining the system. You leave after joining the system on your own wish. So if you leave even before joining the system, it's called bulking. If you leave even, you join and then after some time if you leave, then it's called reneging. And the third and the last, which is what we all have done, is called jockeying. What is jockeying? As literally as the word goes, a jockey. I hope everybody knows what a jockey is. A horse rider, ghudsavar is called a jockey. What does a horse do? Well, it jumps. That is jockeying. In this kind of a system where you are jumping from one queue to another, Are ye fast hai, let's go here. Are nahi, ye slow hai, let's go here. Or the classic, if there are 4 friends, 4 people stand in 4 queues. And then the first one to get the ticket takes the ticket and all of us leave the rest of the queues. That system though we are definitely not talking about. We are talking about jockeying, which is jumping queues. But remember, I told you one thing. Whenever we talk about a queuing system, we will always be talking about a queuing system where only one queue is formed. And sir, if there is one queue formed, there is not going to be any jockey. So can I say jockeying, which in other words is jumping queues, will never happen in our system. Because in our system, there is only one queue. How can you jump queues with one queue? Never going to happen. You need to know these three things for a simple reason that these three things in our system will never happen. In our system, a person who comes will join the system. A person who comes will take service and then only go. So a person who comes will never balk, a person who comes will never renege, and lastly, a person who comes will never have to jockey, because jockeying happens in multiple queues. In a single queue, jockeying does not happen. So let me quickly recap so that I enter into another concept. We are doing queuing systems where you are providing a service for which a queue is formed. When a queue is formed, we study two things: arrival and service. Arrival happens at the rate of lambda per hour and service is given at the rate of mu per hour. Arrival and service are always random. Although they are random, in this randomness, we try to get a pattern out of it, and then we say that arrival file follows Poisson distribution, and I can tell you how many people arrive at the service center at a given time, and service happens randomly, but the time taken to do service is exponentially distributed. Both these follow something called as a memoryless property, where what service the first person gets has nothing to do with what service the second person will get. And what time did the first person arrive has nothing to do with what time the second person will arrive. At the same time, if lambda is less than mu, then the value of rho, which is given by lambda upon mu, will always and always be less than 1. Then why does a queue get formed? Because both arrival and service are random. That is why a queue will be formed. So when you tell me that 5 people get served, but I can only 3 people enter in a system, what if all 3 come together? Then they will have to stand in a queue. No, I will service all 3 in that hour, sure. But these 3 will have to form a queue if they've come in together. Whenever we talk about a queuing model, this is the most stupidest queuing model you will ever see. If all the service centers, no matter how many service centers are, 10 service centers, okay, queue will be only one. There will only and only be one queue that is in the system. You will never be talking about more than one queue. Everybody joins one and only one queue. Well, what if a person comes in and does not want to join the system? Will never happen in our case. If a person has come, will definitely join the system. If a person has come, will definitely join the system, will not leave the system halfway, will take service and then only leave the queue. And lastly, because we are talking about a single queue, people will never ever jump queues. Now that we've understood these aspects, let's move on to a few characteristics of a queue. Now, what characteristics can a queue have? The first characteristic that a queue can have is a population from where the queue is formed. And what do you mean? The population in which the queue is formed could be of two types. One, it could be finite. Another, it could be infinite. What does that mean? I'll give you an example. Let's say that there is a restaurant, and this restaurant is in the middle of a market somewhere or in a shopping mall. Who can come and eat there? Anybody can come and eat there. It's in a shopping mall that's open to all. Or if this is at some local market, anybody can come and eat there. So the population that will come to your system is an infinite population. On the other hand, if the same restaurant is in a corporate park, also known as your canteens, let's say your college canteen, if there is a samosa or a vada pav store opposite your college, who can come and eat there? Anybody can come and eat there. So you have friends from other colleges who can also come and eat there? Yes, there's no problem. But college canteen, without an ID, you can't enter college, and without entering college, you can't eat at the college canteen. Which means that the people that come and eat at the college canteen are limited. Or the queue that might get formed there is a finite queue and not an infinite queue. There is a playground. Yes. People come to play there. Okay. Where is this? Well, it's this big ground somewhere at Mumbai Central. Fine. Or let's say it's the Oval, or it is the Cross Maidan at CST. Who can come and play there? Anybody can come and play there. There is no hard and fast. But if this ground is in your society, which is a gated society, who can come and play there? Not everybody from outside is allowed to come and play there. Only people from your society are allowed to play there. If there is a gym, which is an open to all gym, who can come and exercise at the gym? Anybody can come. Anybody can come, become a member and start using the gym. But what if this gym is in your society clubhouse? And the clubhouse has a rule that only members of the society will be members of the clubhouse, and only they can use the gym. Then can I say the crowd that comes there comes from a limited population or a finite population? So if the population from where the queue is formed is anybody can come and join the queue, then it's an infinite population. But the population from where the queue is formed, where only a certain selected number of people are allowed to come and join the queue, then it becomes a finite population. Similarly, when a population can be finite or infinite, there is something called as queue length. Queue length of a queue can also be of two types. Queue length can also be finite and infinite. Now, can queue length be finite and infinite? Your doctor. Anybody can come and join the queue? Yes. Suppose this is a hospital, a general hospital. Anybody can come at any time to take service? Yes, there's no problem with that. People can keep coming in. I am not anybody to restrict people. But if this doctor has a criteria that I only take 8 people, after the 8th person, they are going to say, sorry, we cannot add you because we have today's limited number of appointments. Or let's say this is a garage where cars get done, and this garage is attached to a big playground next. You go to the guy says, I can't repair your car now, but do one thing, park here, give me the keys. As soon as the car is done, I will give you a call. So is he asking you to not keep the car? No, he's keeping the car. He's going to put it in the queue and call you whenever it's done. But if this is a person with limited parking space, where all the parking spaces are already taken, he will say, you know what, don't keep your car, take it with you. When there is an empty space, I will give you a call and call you. In that case, your queue length becomes infinite or finite. We are never going to discuss finite populations and finite queue lengths. For us, anybody can come and join our system, and anybody can come in at any point where I cannot tell them to not join the queue. Which brings me to our queuing model, or the queuing models that we are going to do. The queuing models that we are going to do are going to be of the type M, C, infinity, infinity model. This is a part of an equation or an expression called the Kendall's equation or Kendall's expression. You don't need to know that also. What is this? When I write down that this is my queuing system, what I'm trying to tell you is this M represents arrival. Arrival is happening at the rate of lambda per hour. And the M tells me that arrival is random, but it is Poisson distributed and arrival is memoryless. So this M represents that arrival is random, Poisson distributed and memoryless. This M represents that service is at the rate of mu per hour. Service is random. The time that I've given you is an average time, is not a fixed time. It is exponentially distributed and it is memoryless. This C tells you how many workstations do you have, or this tells you number of service centers. If you have one service center, then this C is 1. 2 service centers, this C is 2. This is, we have not taken apart from Kendall's equation, so does not have any significance in your bit. This infinity represents that the queue length is infinite, and this infinity represents that the population from where this queue comes is infinite. Now you can have different kinds of queuing models, meaning you see that arrival is randomly distributed. So people arrive at the rate of 3 per hour, which means every 20 minutes people will walk in, but it's not fixed. It is random. Service is random. So random, number of service stations, infinite. You could have a fixed arrival. What is a fixed arrival? Fixed arrival is people who come to take service come at a fixed time. So doctors that call you on appointment. When doctors call you on appointment, you go to them at a fixed time. So arrival is not random. Arrival is fixed. And when arrival becomes fixed, it becomes easier to understand the system. So you could have a fixed arrival, random service, infinite queue length if infinite population system. Or you could have random arrival but fixed service. So what is random arrival but fixed service? I'll give you an example. Suppose you have a place where, let's say, you get a car washed. Now to the car wash, people come randomly, or your bike washing guy, people come randomly. But his bike operation is very standard. Once he starts washing the bike, in exactly 15 minutes he is done. Any bike, give him any bike, small, big, 15 minutes is what it takes for him to wash a bike. So people can arrive randomly, but the service is fixed, 15 minutes per person. Every hour, when I say I can serve 4 people, I am dead sure I can serve 4 people. There is no two ways about it. So I will have a random arrival, fixed service, infinite queue length, infinite population. Or I could have a finite queue length also from an infinite population, or I can have a finite queue length from a finite population, or I can have an infinite queue length from a finite population. I can change this in different ways. You can have different kinds of queuing models. The one queuing model where everything comes to a halt is if arrival is also fixed and service is also fixed. If arrival is fixed and service is also fixed, what kind of a queuing model is this? Why are you even making a queue? If you know when people are going to come in and if you know what service are you going to give them, then there is no queue. Everything is very well planned as it is. People will come, take service, go, next person comes, takes service and goes. There is no waiting, there is no randomness, there's nothing. Everything is very deterministic. It's like people coming to a theatre. People come to a theatre, watch a movie and go. I know people will come at 3 o'clock. Arrival is fixed because the movie is at 3 o'clock. Service is the movie is a 3-hour movie. The service is fixed. So 6 o'clock this will be done. 6:30 next lot will come in. Everything is very fixed. Here there is no queue being formed. But like I said, our standard queuing model that we are going to learn is only one queuing model. We are not going to do different queuing models. Our queuing model is a pretty straight queuing model where arrival is random, service is random. Our people coming to the system come from an infinite queue length and people come from an infinite population. Up until now, whatever I have told you is the background to a queuing system. Nobody, at least at your OM level, nobody is going to ever ask you any of this. Nobody cares, frankly. Nobody. Nobody is ever going to ask you this. What I'm going to do after this is what I want you to understand well, because depending on that, the questions that we are going to do are going to follow. So let's now go into understanding a system or a service station, but with what are we trying to achieve out of this study? What are we planning to, or what are we trying to learn out of a queuing system? So here, now what I'm going to do is, I'm going to draw a system for you with one service center. Correct? So this is my system. There is one service center and people have formed a queue in front of that service center to take service. Correct? Now at the service center, imagine this is an ATM. Or imagine this is an ATM, but then you can get your passbook also printed here. You can deposit money also, you can withdraw money also. I hope everybody's seen those new ATMs now where you can deposit money, you can withdraw money, you can get your passbook printed, everything in one. So it's like a bank in itself. You can drop checks also. Everything can be done on the same machine. So now people come and stand in a queue to get service from this machine. But everybody wants to do different things. Some wants to print their passbooks, but some want to withdraw money and then get the passbook printed. Some just want to drop a check and so on. So there will be one person on the service center. If this is a person providing some kind of a service, then there will be this, the person becomes, see again here, the service center is not what we are concerned about. We are concerned about the people who come to. So when I say that this is a service center where let's say a person is giving you a ticket to something, or you are buying, or this is a doctor, the doctor is a server. The doctor is a part that is providing service. So the doctor becomes a server. I am concerned about the people who are taking service. So even if it's an ATM, it's a server. Even if it's a doctor, it is a server. This entire thing constitutes my service center. So this is my service center where people come to take service. What are we concerned about? Or what are we trying to study out of this? This all of us have done. And that is, if you go to a doctor at a certain point of time, you ask your friend, or if you are going to that same doctor, you ask your friend, number one, कितना बड़ा लाइन होता है? बहुत लोग होते हैं क्या? Number two, कितने टाइम में काम हो जाता है? मैं पासपोर्ट निकालने, I am going for my passport. How long do you think the queue is? How early should I go? How long does the verification take? So you are asking these questions only, no? So we are going to ask two things. The first thing that we are going to ask is length. And the second thing that we are going to ask is waiting. The two things that anybody who is going to take a certain service is concerned about is what is going to be the length of the queue that I go to, and for how long will I be waiting in the queue. And this is exactly what we are going to study. Now, when you look at the service center, can I say the service center or the queue is divided into two parts, or the people are divided into two parts? What are the two parts? Well, there is one person who is taking service. So question, is that person in the queue? Well, yes, but no, the person is not in the queue. The person is taking service. Oh, but this person is still not gone. He or she has not finished the service. Okay. So this gives rise to two things. Number one is length of the queue. And number two is length of the system. Similarly, I am concerned about the waiting in the queue and the waiting in the system. What does that mean? How long is the queue? Now, when you ask me how long is the queue or the length of the queue, you are asking me how many people are waiting in the queue. But when you ask me what is the length of the system, you are asking me if I shut down the entire system right now, how many people are there in it? Well, then there are these people who are standing in queue and another extra person who is getting the service. So that person is not in queue. That person is getting service. So if in this situation I ask you what is the length of the queue, you will tell me there are 1, 2, 3, 4, 5 people in the queue. But what is the length of the system? Well, 1, 2, 3, 4, 5 and 6 people in the system. What if there was another service center, another service station? So then there would be one person here and one person here. Now what if I ask you what is the length of the queue? Well, length of the queue is 1, 2, 3, 4, 5 people. Perfect. What is the length of the system? Well, the entire system has these 5 people along with these 3 extra, 5 plus 3 is 8 people in the entire system. So length of queue is represented as LQ. Length of the system is represented as LS, and both are related to each other. How are they related? Can I say the entire system is nothing else but the people in the queue plus the people being served? So length of the system is nothing else but the entire queue plus the people being served. We are concerned with two main parameters, length and waiting. By length I mean what is going to be the length of the queue and how many total people in the system or length in the system. By waiting I mean how many people waiting, how long is it going to take for me to wait in the queue. And waiting in the system means I will wait in the queue, take the service and then go. So for example, if I was in the queue for half an hour and the service took 10 minutes, then waiting in the queue is 30 minutes and waiting in the entire system is whatever I was doing in the queue plus whatever it is going to take for service. So 30 minutes plus 10 minutes for service is going to be 40 minutes in the system. This length that we talk about is number of people. So when I talk about length of queue, I am asking you how many people in the queue. When I am asking you length of the system, I am asking you how many people in the system. When I ask you waiting, which is WQ, which is waiting in the queue, and WS, which is waiting in the system, I am asking you the time in hours. So waiting in the queue is how long do I have to wait in the queue in hours, and waiting in the system is how long am I going to be in the entire system, time based. So what is the time that I am going to stand in the queue, and what is the time that I am going to be in the system. Time in the queue or waiting in the queue, which means for how long you were in the queue, and in the system means for how long were you in the queue, plus how long did it take for you to get service. These are the only 4 aspects, and I am going to show you this only on the basis of one basic formula. What your institute material has done is terrible on a different level. So I want you to pay attention to what I am doing. A quick recap. What are we concerned about? We are concerned about 2 things. How big is the queue that is being formed? And if a person comes in, how long does the person have to wait? Like for example, for a 1 minute thing, if that person has to wait for 30 minutes, it's wrong. Your system is flawed. So I want to learn 2 things. One is length and waiting of the queue and of the system. What is queue and the system? Well, this part is the queue, while the entire thing is the system. So when you ask me length of the queue, I am only looking at people standing in the queue who have not yet gotten service. But when you talk about length of the system, I am talking about people in the queue and people getting service. When I ask you waiting in the queue, I am asking you for how long do I have to stand in this queue till I reach the service person or the server. When I ask you waiting in the system, I am asking you how long did I wait in the queue, and then how long did it take for me to get service. This is a number, this is time, and is always in hours. So here whatever you get here is time, which is always taken in hours. Now to go ahead with the formula proofs and deriving the formulas and writing them down, before that I want you to understand something called as utilization of your system. What do you mean by utilization of your system? Let's go back to the first example. Remember I told you people enter at the rate of 3 per hour, correct? And can be served at the rate of 5 per hour. Fantastic. People arrive at the rate of 3 per hour and can be served at the rate of 5 per hour. Is that correct? Yes. If people are arriving at the rate of 3 per hour and you can serve them at the rate of 5 per hour, can I say that? There is time when you are not doing anything. How come? I'll give you an example. Let's imagine this system. 3 people come in. When do they come in? Let's say the first person comes in at 0. Then the second person will come in at 20 minutes. Oh, sorry. And the third person will come in. Let me write that again. At 0 minutes, the first person comes in. At 20 minutes, the second person comes in. And at 40 minutes, the third person comes in. So, people arrive at the rate of 3 per hour. So, after 40 will be another 20 minutes. But that next person will be the 0th. Or what you can do is, you can do this reverse. You can start writing it with, let me do it on a new piece of paper. The first person came in. You opened the store at 0, but the first person came in on 20 minutes. The second person came in at 40 minutes. and the third person came at 60 minutes. And this is how I said that there are 3 people on an average per hour. Now I know and I agree with you that this is not fixed. This is random. Okay. Then just try to understand that 3 people walk in every hour. What is your rate of service? The rate of service is 5 per hour. You can serve 5 per hour. Okay, so let's do the time-based distribution of this. Start at 0, 5. 60 divided by 5 is 12. 12 minutes the first person gets served. Then 12 minutes the second person gets served. Then 12 minutes the third person gets served. Then 12 minutes, 12 ones are 12, 12 twos are 24, 12 threes are 36, 12 fours are 48, fourth person gets served, and 12 fives are 60, the fifth person gets served. But I'm not going to serve 5 people, I'm only going to serve 3 people. Fine then. Can I say in 1, 2, 3, which is in 36 minutes, technically your work is done. 36 minutes, the third person will come and get served at 48 and you are done. But can't you serve 2 more people? Yes, I can. 2 more people will be 12 plus 12 is 24 minutes extra. Then can I say in a span of 60 minutes, you will spend how much? You will spend around 36 minutes serving 3 people. And the rest of the 24 minutes, you will have to sit idle. Why? So because you only said you should be capable of serving more people than arrive. Yes, I told you. But then can I say that your system is not working efficiently? You are taking a salary for me for 60 minutes. But you are working only for 36. So your actuals are for only 36 minutes. Correct. So can I say I am utilizing you for 36 minutes out of 60. What is 36 out of 60? 36 divided by 60 is 0.6. Multiply that by 100 is 60%. So can I say you are only 60% utilized? Rest of the 40% of the time you are wasting? Correct. But sir, then this is happening because the arrival rate and the service rates have to follow a certain relationship, and that is arrival should always be less than service. Correct. But this utilization of the system will tell you everything about your system. This 60%, or in other words 0.6 that I found, I technically didn't have to do all of this to tell you that, oh, people are arriving, or 3 people are arriving, you can serve 5. If you can serve 5, technically for 3 people it will only take 36 minutes. Rest of the 24 minutes you are not doing anything. So 2 people's time is wasted. But that has to be there because I have to be able to serve more people than that can arrive, because this is going to be random. There might be an hour that nobody arrives, and then there might be an hour where 6 people will arrive. So I should be able to serve more than what arrive. So this utilization that is happening, this 60% that you are utilizing, does not need to be found with all of this. There's one simple thing that you could do. You could find rho, which is lambda upon mu. Lambda is 3 and mu is 5, which is 0.6. That's it. You are capable of serving 5, but you are only serving 3, which means you are only working 60% of your potential. Well, what about the rest of the 40% time? 40% time you are idle. I can't help it. The system was created in that way. And if you are serving more than people that come, there is always going to be that there is going to be an idle time. And this utilization, known as rho, is a very important parameter in queuing theory. This parameter will basically tell you or give you everything about your system. But where does this row come from? Well, it comes from the value of lambda. So can I say a queuing system has three parameters. Parameter number 1, lambda, which is the arrival rate. Parameter number 2, which is the service rate. And parameter number 3, C, which is the number of systems. And if you give me these three things, I can tell you anything about the system. So if you tell me that people arrive at a rate of 3 per hour and I can serve at a rate of 2 per hour, but I have 3 systems, well then simple. If you have 3 systems, every system can serve 2 people, then you can serve a total of 6 people per hour, not 2 people per hour. And with that, I can tell you anything about my system, starting with how well is my system utilized. It's basically lambda upon mu. Well, I lied. It's not lambda upon mu. It is lambda upon mu C. Well, what is C? Simple. See, if there is one service center, then if I tell you that you are serving 5 people, then I'm serving 5 people. Simple. But if I put 2 service centers where each is serving 5 people, then I can serve a total of 10 people. Didn't my service rate increase and became double? Well, here I have 3 centers, so my service rate will triple, will become 3 2s are 6. And that is why this value of rho, which is how well utilized is your system, will give you everything you need to know about the system. I'm going to do a quick recap and wind up this session, because from the next session onwards, I'm going to do formulas and then eventually questions. So, what are we doing? We are doing queuing theory. What are we doing in queuing theory? Well, we are trying to find out how people arrive and get served, so that if there is any improvement that I can do, or if I have to do any cost-based calculations, I will do them. Fine. Arrival happens randomly at the rate of lambda per hour. Service happens randomly at the rate of mu per hour. But this randomness, because we have to study and understand and derive inferences from it, we assume that the arrival follows Poisson distribution while the service follows exponential distribution, and both are memoryless. The arrival rate should always and always be less than the rate at what you serve, because if the arrival rate becomes more than what you can serve, then there will always and always be a certain number of people who will be denied service, which means your system is not a good system. When we talk about systems, no matter how many servers we talk about, we will only be talking about a single queue in front of the servers. We will not be talking about multiple queuing systems. And now that we've spoken about multiple queuing systems, let's talk about a few very important things which you need to know to understand that this is never going to happen in our system. Bulking. Anybody who comes will join the system and take service. Nobody will come, look at the queue and leave. No. Reneging. Anybody who comes will join the system and take service. There will be nobody who will come and stand in the queue and leave halfway. No. Jockeying is jumping of queues. Nobody who comes will jump queues. Everybody and everybody will stand in one queue, and because we assume a single queuing system, our system will never jockey. When you talk about queue lengths, you can have populations that from where people come in. You can have a finite or an infinite population. Queue lengths can be finite or infinite. We are always going to assume an infinite population with an infinite queue length. We are doing the most general form of a model. And that is why our model is going to be an MMC, infinity model, where we are going to talk about random arrival, random service, C number of queuing systems with an infinite population and an infinite queue length. Up until here, nobody is going to ask you anything. For me, what is important is from here. When you talk about a queuing system, what we want to learn or know about the queuing system is two things. Number one is the length of the queue, the length, and the other is waiting. Length of the queue and length of the system, waiting of the queue and waiting of the system. Length of the queue meaning how many people are in queue. Length of the system meaning how many people are in queue plus whoever is getting service. That is length of the system. This is always a number. Waiting in the queue is how long will I be in the queue. Waiting in the system is for how long will I be in the queue plus how long will it take to get service. This is time based and is always in hours. What we are going to know or what we are going to judge everything on is how well utilized your system is. And this utilization is given by the values of lambda and mu by a simple calculation, and that is utilization is given by rho. That rho is nothing else but lambda upon mu. This will tell you how well utilized is the system, and depending on how well utilized is your system, I will tell you everything else. I will tell you what average length of a queue is, what average length of number of people in the system are, how long on an average will it take for you to stand in the queue, and how long will it take for you to go take service and come out of the system. This value of rho, if there is only one server, then it's lambda upon mu. But if there are 2 servers or 3 servers providing you the service mu, then the service will double or triple, and that is why it becomes rho is lambda upon mu c. If you are 60% occupied, it means you are 40% idle. So if rho is utilization, then percentage of idle is 1 minus rho. If you are 0.6 utilized, then you are 0.4 unutilized. Or in 100 hours, 0.6 means 60%. So in 100 hours, if you are sitting in the shop, 60 hours you were working, 40 hours you were idle. So my system's utilization is rho, which is lambda upon mu minus c, and my system's idle is 1 minus rho. With this, I am ending this session. In the next session, I will introduce formulas and then we will move into questions. And that part is going to be very important for me. Because if you understand the formulas and the working, that's it. All this, nobody's ever going to ask. Thank you very much. I'll see you in the next session.